In this video, we want to talk about how to solve or really write equations when we're given things as a percent. So if I say I start with $10 in my account and it grows at a 3% rate for the next however many years, or the value of my car decreases at 20% every year. So when we're given something like that and we don't hear the word double or triple, then we have to use this version of our formula. So y equals a times 1 plus or minus r raised to the power of t. A is still my initial amount. R, though, is our rate in decimal form. So if I'm given it as a percent, I have to convert it into a decimal by moving my decimal point 2 spaces to the left. T is the number of time periods. The plus or the minus is just if I'm increasing, I would use a plus, and if we're decreasing, we would use a minus. So now let's take a look at an example. So there's this thing called the basal area of a tree, and it's the cross-sectional area on the trunk 4.5 feet from the ground. Not that any of that matters. However, if we have an area of a tree trunk and it grows by 1.5% each year, it started 10 square inches. They want us to write an equation to show the basal area as a function of time. Well, we know that because they gave it to me as a percent, I'm going to use this form of my equation. So we need our A and we need our R, and we need to decide our sign. So I'm going to write those things down. So our sign, I have to decide, is it growing or getting smaller? Well, it says the word grow, so I know I'm going to use a plus sign. A is my starting value. It tells me right here that it started at 10 square inches. And R is my rate. It says 1.5%. But we have to remember that the rate has to be in decimal form. That doesn't mean it has a decimal point in it. It means it's not written as a percent. So to do that, we scoot our decimal point to the left 2 spaces because we're really dividing by 100. So if we scoot it twice, we would end up like this. Now that we have all this information, we just substitute those values in. So y equals 10 times 1 plus 0.015 to the power of t. And I can simplify this by adding it together. So we get y equals 10 times 1.015 to the t. This will let me find out the basal area for a given year. So if I want to say, hey, 10 years from now, how big is the basal area? Well, I can substitute 10 in for t and type this into my calculator. Oh, you can't really see that, my bad. Meow. That's good. Okay. This one, just so we know, is 100%. That means it doesn't change. Like if I have 100% of what I had last year, I have the exact same amount. It didn't grow or decay. That's why that 1 is always there. So now we're going to look at an example of exponential decay instead of exponential growth. So according to a U.S. Geological Survey study released last year, the population of frogs, salamanders, and other amphibians are declining at an average rate of 3.7% each year. It is estimated that there are currently 1,000 amphibians in a Missouri habitat. So I wrote down the general gist of that example here. Our population is declining. That's important because that tells us that we're decaying as opposed to growing. The average rate is 3.7% each year, and it's estimated that there are currently 1,000 amphibians. So because it gave me a percentage, I know I'm going to be using my percent increase decrease formula. In order to use this, I need to know the A, my initial value. I need to know the R, which is my rate, and I need to know the sign. Am I growing or am I decaying? Another word for decay, just so we know, is depreciation, in case you hear that as well. So in my situation, my A is what I start with. My current amount is 1,000 amphibians. The R is my rate, but it has to be as a decimal. So they give me 3.7%. Now remember, I said just because there's a decimal doesn't mean it's in decimal form. To actually turn this into decimal form, I'd have to divide by 100, which would move my decimal point 2 spaces to the left, so 0.037. The sign, because it's declining, would be subtraction. So now we're going to go ahead and substitute this information into our general form. So we get y equals 1,000 times 1 minus 0.037 to the power of t. And again, if that's an x, that's okay. It still just represents our independent variable, which in this case would be time in years. So this would be our equation that tells us the relationship of the number of amphibians as a function of time. Now, if we wanted to, we could combine those two and actually do 1 minus 0.037, which would be fine. So now we can use this equation to find things. For example, if they want to know how many amphibians will there be in 10 years, well, that means t is 10. So I'm going to substitute that into our equation for t. And we can type this into our calculator to find out that there would be 685 amphibians after 10 years. So we started with 1,000, but after 10 years there will only be 685 remaining. So that's it.